All right, so we're recording. All right, so before I go through the key and the rubric, I want to take a quick look at the calendar here. So we started back to school on the 22nd. So 1 week, 2 week would be the 7th. 3 week, 4 weeks. So we were in it was 5 weeks when we took our first one. I think I'm going to go another 5 for the next one. That'd be 2, 3, 4, 5. So November 2nd will be the next one. And that means that your last test will be the last regular class, which I can't remember exactly when that is. I think it might be December 7th. All right. I'm remembering, I think the week of the 23rd is Thanksgiving, just looking at it. So it's roughly every 7 week or every 5 weeks by the calendar, and then we'll have our cumulative final during the week of the 14th. All right. Okay, so that's the deal. And one of your 3 in class, your lowest of your 3 in class test scores will be dropped from your overall grade. All right. So let's go ahead then and get back here. Could you hit the lights for me, Randy? I'm sorry. You're all set up. I could. Okay. So the first question is a modified David and Goliath. David and Goliath are pushing a frictionless car of mass M, initially at rest. Goliath, strong but out of shape, applies a forward push with the magnitude F naught e to the minus 2t over tau, where tau and F naught are constants. David, weaker but with more endurance, applies a backward push of 1/2 F naught e to the minus t over 2 tau. Draw the figure, free body diagram, state Newton's second, and apply it to the system. Find a soluble ODE. Okay, let's do that. All right, so I've got a car, I've got Goliath pushing forward, and I've got David pushing back. I'm going to go ahead and let x at t equals 0 be the origin of my coordinate system. That's the positive x direction for me. Figure, okay, now I need a free body diagram. So the car will be my system. It has a force from Goliath. It has a force from David. It has weight, and it has a normal force on it, okay? Things to remember, because I know some of you guys transferred in from other schools and stuff, and they did free body diagrams maybe differently. We have free body diagrams with all the arrows coming out of a single point, and that point represents really the center of mass of whatever object we've chosen to be our system, which in this case is the car, okay? So we need those to be outgoing arrows in the future. All right, so I got the free body diagram, state Newton's second law. Sum of all x components of forces is equal to max. Sum of all y components of forces is equal to may. That is Newton's second. And what I get from this particular system is F Goliath, where these symbols on here, the direction of the forces are in the arrows, so all these letters on here represent magnitudes. All right, so minus the magnitude of the force from David is equal to ax, and normal force minus weight of the car is equal to 0, because it's going to move purely horizontally. Okay, and so now I've applied Newton's second to my particular system. Now I need to find a soluble ordinary differential equation. This equation is trivial, so we'll work on this side. the magnitude of the force from Goliath is F naught e to the minus 2t over tau. And the magnitude of the force from David is F naught over 2 times e to the minus t over 2 tau. And that's going to be, I know how I'm going to solve it already, so I'm going to write that as dv dt. Okay, that's fine. You could have had x double dot there or v dot, whatever. So in this case, that's what I've got. So the only variables are going to be, the dependent variable will be t, and the dependent variable will be as a function of time. The independent will be t as a function of time, and that's an ordinary differential equation. So I'm done with that. Okay, so I think, let me check and make sure that I have this correct so that I'm not going to propagate any errors in my solution. Because you know how I am. All right, looks so good. So far, so good. All right, so then for part B, I'm asked to find and simplify the car's velocity as a function of time, v of t. All right, so I'm going to separate my variables. I'll get m dv is equal to f naught e to the minus 2t over tau minus f naught over 2 e to the minus t over 2 tau quantity times dt. So I'm going to go ahead and distribute my dt like so. And then I'm going to notice that I have to integrate both sides from initial to some arbitrary value t in order to get velocity as a function of time, which is what I want. So I need to do that here. So I'm going to go from initial to final there, initial to final here, and initial to final here. And that's initial to final variable, where the variable of interest is the one whose increment I'm integrating over. So my initial velocity, if I look at the statement of the question, it says that my car is initially at rest. So that means I'm going to go from v initial, which is 0, to v final, which is v at some arbitrary time. I'm going to let my initial time be my origin of my time coordinates. So I'm going to let t initial be 0 and t final be time. Similarly here, 0 to t. Okay? All right. So on the left-hand side, I am going to get m, v as a function of time, minus m times 0. And on my right-hand side, I've got some math to do. So I have an e to the u du that I would like to perform the integral of, because that's what I know how to do. But in order to do that, I must multiply my dt by negative 2 over tau. And in order for my equal sign to work, I'm going to need a negative tau over 2 out front here. Similarly here, I'm going to need a negative 1 over 2 tau, which means I'm going to need a negative 2 tau out front here. Okay. So I have negative tau over 2 f naught. Now I have e to the u du, which I can integrate. It gives me e to the u. So that gives me e to the minus 2t over tau minus, I'm going to evaluate from 0 to t. So I've already evaluated at t here. So I now need to evaluate that for when t is equal to 0, which gives me e to the 0, which is 1. Is that okay, or am I skipping too many steps? Is it all right? Okay. All right, so then I've got a minus negative 2 tau, which is plus 2 tau, times f naught over 2. Again, I've got an e to the u du set up here, so I have e to the minus t over 2 tau minus e to the 0. Okay, so m times v as a function of time is minus f naught tau over 2. Maybe I should start gathering up my terms. Should I start gathering up my terms? We'll see. Okay, so I've got times e to the minus 2t over tau minus 1. And plus, I'm just going to do my math the silly way, f naught tau over 2. And I'm, oops, yeah, so I still have a 2 there, but I'm just going to keep my 2 out front because that's kind of nice. So that gives me 2 e to the minus t over 2 tau. Minus 2. I think I like that. And a minus sign out front. Okay, so I'm going to go ahead and distribute this minus sign that's out front so that I don't make a math error because I know myself well. All right, so I've got f naught tau over 2 times, I want my thing in my parentheses start with something positive, so I'm taking that term first, 2 e to the minus t over 2 tau minus e to the minus 2t over tau. And then I've got plus 1 minus 2, so that is minus 1. And that is equal to mvt. So if I want to write this as v as a function of time, that's fine, but I need to put my m over here. Now let me check and see if I'm doing okay here. 2. Okay. It looks all right. Is everybody okay with that? Can we second that? All right. Oh, I should have been talking through my rubric. I'm sorry. So, okay, things that could have gone wrong in part A are that not having a free body diagram or having a free body diagram that isn't a free body diagram, starting from the center. That would be at least minus 2 points. If you wrote this not as a differential equation, but with just a there, that was minus 2 points. I needed it to be a differential equation. Other things about, mishandling Newton's second, were different amounts off. I don't know what to say. Using the wrong expression for these forces, that was minus 2. Now, as you propagate that error through, I didn't take off for it, but there's having these terms written like that. Okay. Would be minus 2 if you had an error at that stage. And so I know that's the type of detail that we're going to have to get there to being able to get that right. All right, and then on this expression, things that were common were dropping the m, which was 1 point off, not noticing that we started that initially at rest is code for v naught is 0. That's a point off. There were algebra errors that could be 2 points off. Not simplifying this would be a point off. And then, but in general, having an error from this step to this step of a calculus nature was 3 points off. Okay? All right. All right, so are there any questions at this time, or can I move on? All right, so then let's move on to part C. So part C states, find and simplify the car's location as a function of time. Okay. So in this case, I'm going to start from my expression for velocity. I'm going to rewrite it as dx dt is equal to f naught tau over 2m times 2e to the minus t over 2 tau plus, or minus, I'm sorry, e to the minus 2t over tau minus 1. Okay, and some of you guys wrote, it's probably more common that that wasn't there and this was written as 1/2 and this was written as 1/2. So I'll proceed in that way because that was the most common expression. All right, so now I need to find location as a function of time. So I'm going to separate my variables by multiplying both sides by dt. And my equality will still hold nicely if I integrate both sides from the initial value of the variable to the final. So initial to final here and initial to final on t. So I'm going to choose my coordinate system that its initial location was 0, which I can do without loss of generality, as many of you all noted. And my final location then will just be my location at some arbitrary time, so long as I note that my initial time, I can go ahead and call that 0, as I did before as well, and let my final time be called t. Okay, so on the left-hand side, I get x at time t minus 0. And on my right-hand side, I've got f naught tau over m times the integral from 0 to t. And I'll go ahead and make that as 3 terms. We'll see how this works. Okay, so I've got e to the minus t over 2 tau times dt minus 1/2 e to the minus 2t over tau dt minus 1/2 dt. Oops. Okay. All right. So again, I would like these to be the form e to the u du. In order to do that, I need a negative 1 over 2 tau here. So I need to multiply out front on this guy by negative 2 tau. Negative 2 tau. That's messy, I apologize. Okay. And then similarly here, I need a negative 2 over tau, which gives me a negative tau over 2 that I must multiply out front to keep my equality. And I think now I've got everything to the form I need it. So x as a function of time is equal to f naught tau over m. Negative 2 tau times the integral of e to the u du, which gives me e to the minus t over 2 tau. That function evaluated t, which is already done, minus that function evaluated 0, which gives me e to the 0, which is 1. Okay, plus tau over 4. And I've got e to the u du, so again, e to the minus 2t over tau is my function evaluated at t minus the function evaluated when t is 0, which is e to the 0. So minus 1/2 times t. Okay. So now I just need to algebraically simplify this thing. F naught tau over m. So I've got I want it to be a positive term up front, but I guess it doesn't really matter. So I've got, all right, minus 2 tau e to the minus t over 2 tau. And then I'm going to keep that next term for later, plus tau over 4 e to the minus 2t over tau. And keep that one. We can deal with that now. So now I've got a positive 2 tau for my first term here, and a negative tau over 4. So that's positive 8 tau over 4 minus 1 tau over 4. So that's positive 7 fourths tau minus 1/2 t. Okay. And I'll go ahead and put a box around that because that's my simplest form. Errors that could be made there. Again, if we had a calculus error, which generally occurred, most generally from here to there, but generally occurred here because most of the errors were with applying Jacobians to get our expressions to the form of e to the u du correctly, or I don't know, other errors like that would be -3, all right, or not properly evaluating your integral limits and stuff like that. All right. Other things that could happen would be, again, not noting that the initial velocity with initially at rest means v naught was 0. That would be -1, or not simplifying, which would be -1. Okay. And then for part D, what happens to the car's location when t goes to infinity? All right, so clearly in this case, I am asking you to evaluate the limit of x as a function of t. And I've got f naught tau over m. I'm just going to evaluate my limits here. When t goes to infinity, I get e to the minus infinity times something, but that's 0. This guy, again, will go to e to the minus infinity times something, which is 0. And this guy will just be a constant for 7/4 tau. And this last term, it goes to minus infinity when t goes to infinity. So the answer here is that then this limit goes to -infinity. Looking at my original figure, that means that David wins the push of war. Okay. Things that could happen there. Sometimes the expression that you got for this limit didn't agree with your conclusion, so that would be -5. Or maybe not applying this limit mathematically would have been -5. Those are the two things I've made notes about. Are there any questions about that? Okay. All right, then let's move on. Okay. So number 2. An object is thrown vertically up the initial speed v naught in a linear medium. Measuring y upward from the point of release, draw the appropriate figure, free body diagram, state Newton's second law, apply it to the given system, and find a soluble ordinary differential equation of motion. You may use the substitution vt, v term is mg over v. All right, so let's go ahead and do it. So, oh, that's kind of a mess. All right, so this is number 2, part A. All right, so I have an object that was initially thrown upward with some v naught. Now, I didn't draw that arrow on the free body diagram because it is not a force, and only forces belong on the free body diagram. This is my free body diagram for my system, which is just a ball, so it kind of looks good. I've got a downward force of weight, and I've got a downward force of B times V. That's the drag force. And I'm going to go ahead and allow that up is the y hat direction in my figure, and that the initial location is y equals 0. Keep that in mind. All right. So now I've got an appropriate figure. I've got coordinates. I've got a free body diagram, which is the same as my figure because it's just a ball. I need to state Newton's second law and apply it. Newton's second law in the x direction is going to give me 0 equals 0, which is too trivial to mention. But in the y direction, I do have something interesting happening. So I've got negative BV, and yeah, you could note that this would be a VY, but since it's a one-dimensional problem, just calling it V, noting that that'll be V is positive when it's directed up in this expression, and it's negative when it's directed down, meaning the drag force would be directed up. So that's all taken care of in this sign. Okay, and just to be very clear, for right now I'll use the subscript Y, but in the future I won't use that. Minus mg is equal to m times Vy dot. And I already have that then as an ordinary differential equation, but that's not the equation that I solved, so I'm going to keep on going. So I'm going to note that I was invited to use mg over b as V term. So I've got a minus b out front times Vy minus mg over b, which I've been invited to call V term. I'm going to shorten that as V sub capital T. And that is equal to m times d Vy dt. That is an ordinary differential equation as well. You could have stopped at the previous step as well. Okay, so I'm done with part A. Now part B asks me to find the object's velocity as a function of time. So I have negative b times v as a function of time minus v term is equal to m times dv dt. I'm going to multiply both sides by dt to separate my variables. And then I'm going to integrate both sides from initial to final. So I've got a negative b. No, I'm not. That's not right. I didn't separate my variables. They won't be separated until I get my v stuff over here. So let's not do my integral yet. Not integrating yet. Still trying to separate my variables. So I've got minus b times dt on the left-hand side. And I've got m times dv, which depends on v, but I also have this guy, which depends on v, so I need to put it over there. 1 over v minus v term dv. Now I have my variables separated, and I can integrate from initial to final on both sides. My equality will be fine. Initial to final, initial to final, and that's on this variable here. And so I've got this guy going from my v initial value, which was called v naught, my statement of my question, and v final, which will just be my v as a function of time. I'll just call it v, but you can put it that way if you like. My t initial I'll call 0 without lack of generality, and my final time I'll call t. All right, so I've got minus v times t minus 0 for my left-hand side is equal to m. So this is a 1 over u du, where my u is v minus v term, because in that case du is just dv, because v term is a constant. Okay, so I already have it in the form of 1 over u du, but just remember that my u is v minus v term. And so 1 over u du gives me natural log of u, and I guess I can write that as v minus v term, which has to be evaluated from v naught to v. I'm sorry, it sounds like a lot of you guys are bored, which is fine. I'll just try to go quick, or if I can. All right, so I've got minus bt on this side, and I'll go ahead and divide both sides by m, so that's over there as well. And on this side I've got my natural log of v minus vt divided by v naught minus vt. Noting that the difference of two natural logs is equal to the natural log of the ratio of the two. I want to solve for v as a function of time, so I've got to get v all in on one side of the equal sign. So I'm going to take e to the on both sides of the equality here. E to the, on the left-hand side, I've got e to the minus bt over m. On the right-hand side, e to the natural log of something is just the argument, so I've got v minus vt over v naught minus vt. Why do I have, I don't feel like this should be a minus sign. So I'm going to go back there and correct that because I just noticed that I've been making an error through the whole thing. That's okay. It happens to me too because I know those are the same sign, so I screwed that up. All right, so I need to evaluate this now. I get V plus VT. All right, I apologize. Okay. So now I need to get V all alone. And I get V naught plus VT. I'm just going to flip things a little bit. V plus VT is equal to the quantity V naught plus VT times e to the minus VT over m. And V is equal to minus VT plus V naught plus VT times e to the minus VT over m. I'm going to put a box around that, but I'm also going to check it because I did make an error that makes me nervous. So I want to make sure that everything here is okay. So when t is 0, I do indeed get V naught. And when t goes to infinity, I get negative VT, as I should. So I think that I actually did it right, and I apologize. I am, as you know, that's kind of my thing to make an error, but okay. And I'm still nervous, so I'm going to have you guys tell me, is this the expression? All right, okay, great. Okay. So then part C asks, find the object's location as a function of time. Y as a function of time. All right. So I'm going to use the expression I got from part B. Oh, by the way, common errors on that one. I didn't even note any common errors. I don't think anybody made any errors. Well, nothing common, nothing that was repeated. So, all right, anyway, I'm going to start from my previous expression, which is Vy is a function of time, which is the time rate of change of my y coordinate, is equal to minus V term plus V naught plus V term e to the minus Vt over m. I'm going to multiply both sides by dt. All right, and I already have my, in this case now they actually are already separated because I don't have any y dependence over here. So I'm going to integrate from initial to final. The point of release, I'm going to let be y equals 0, and then I have y as a function of at value time. It's my final. Integrate from initial to final. Point of release, time of release I'm calling 0. Later time I'm calling t. All right, so I get integral of dy is y, which I evaluate from 0 to t, so that gives me y of t minus 0. Okay. And on the right-hand side, I get minus vt times t, which I evaluate from 0 to time, so minus 0, plus v naught plus vt times the integral e to the minus bt over m dt, which I want that to be e to the u du, so I have to multiply by minus b over m for that to work, which means I have to have a minus m over b here for those two to be equal. And so I've got y as a function of time is equal to minus vt times t minus m over b, v naught plus vt times, oh, that's from 0 to t. So e to the u du gives me e to the u, so that is e to the minus vt over m, which I have to evaluate at t, which is just that, minus its value when t is 0, which is 1. And I think that is, that's simplified enough for me. So, okay, I'm just going to keep that expression there. All right. And then part D. I'm asked to find the time for the object to reach its highest point. At the peak of its motion, it's not going up anymore, it's not coming down yet. So at that point, v is equal to 0. So I'm going to use this expression up here. 0 is equal to minus v term plus v naught plus v term e to the minus vt over m. I need to solve that for t. So I've got v naught plus vt e to the minus vt over m is equal to v term. I'm going to look at that for a second. Okay. Divide both sides by v naught plus v term. That goes away. All right, so I'm going to take natural log of both sides. And I get negative bt over m is equal to the natural log of vt over v naught plus vt. But if I want that to be a positive sign, I can make that v naught plus vt over v naught over vt, sorry. And I get t is equal to m over v. Natural log v naught plus vt over vt. Sorry, that's not even showing. I apologize. There's your expression. And I put a box around that, and I look at my rubric, and it looks like you guys did a great job at that one. So, all right. So, again, that was an 80-point exam. I think that everybody did fine. Even if it is your dropper, that means you're behind the 8 ball, which is obviously kind of a, you know, an okay place to be in terms of adrenaline. That is actually somewhat helpful if you need it. Otherwise, just, you know, again, I would recommend if you did do well, don't ease up on the next one, all right? So, but basically you guys are all totally on track, and I am, for once in my life, happy after grading a test. It's been a while. All right, guys, get out of here, I'm brain fried. You've already seen everything for the homework, so you should be able to work on that to your heart's content. We'll finish the other chapter, chapter 3. On what day is today? I am really brain fried at the moment. On Wednesday. All right, see you guys later. Even if you didn't get a good grade, I just want you all to know you really showed me what you could do, and you're doing fine. So, looks great.